In this video we're going to look at centripetal acceleration. Now the idea behind this is that if we had a particle and it's travelling in a circle, so there's a circle there, it's just travelling in a circle there. If we take a point P, so that's a little particle, then if we were to look at the centre of the circle here, we call the centre circle O, then it'll have a radius R. Okay, now if it's travelling say around in this direction, then the contention is that there's actually an acceleration on this particle which is tending to trying to collapse the particle into the centre. Okay, so the acceleration vector is in that direction. Okay, so that acceleration is what we call the centripetal acceleration, so we say AC, and we're going to show that that centripetal acceleration can be given by the equation equals minus v squared upon r. Okay, so that's what we're going to show today. And we're going to go through it in a couple of different methods. Okay, so another thing is that v, the velocity vector, it points tangential to the direction of motion in the circle. Okay, so that's vector v there, so round at this point here, for example, it would be a tangent to that point there, so it would be in that direction, and round at this point here it would be that direction, and that acceleration be given by that velocity, which is the magnitude of that vector squared all upon the radius, and the negative sign just tells you that it's pointing, the acceleration is pointing towards the centre. So as this turns round here, it's trying to collapse this point P into the centre O at all points. So a point round here will have an acceleration pointing directly into the centre, and it's called centripetal acceleration because centripetal means centre seeking, so the acceleration is seeking the centre of that circle. So let's go ahead and we'll go and have a look at a couple of different ways of deriving it. So this is method number 1. Okay, and each will have their own merits, okay, and disadvantages. So if we were to look at, say, a point, if we look at an arc of a circle, so let's say that angle is theta, that length is r, then this arc of a circle, so that's just a big circle around like that, and this arc here is length s. So if the theta is measured in radians, then we can say that the length s will be equal r times theta. Okay, now don't get confused about that. All that's really telling you is that if the circumference of a circle c equals 2 pi r, well, if we make r equal to 1 to simplify it, we could say the circumference of a circle is 2 pi, so that's just a number. The circumference of a circle of radius 1 is 6.28. So if we look at the distance travelled round half a circle would be half of that, which is 3.14. A quarter of it would be a quarter of that pi, a fifth would be a fifth of that pi, so we can take any ratio of that value of the circle. Now if we choose to take the ratio of theta, then we could say that this length s would just be equal to that value of theta whenever r equals 1. Now if we then add the value of r into it, so we say s equals theta, if we add the value of r into it, then r would just have the effect of, say for example, r equals 2, it would just double it. If r equals 4, it would be 4 times it. Okay, so we just have the effect of adding r into this equation, so then you would have the circumference of the circle that would be given by r theta. Okay, so that's where that comes in. Now what we're interested in is the instantaneous velocity. So in order to get the velocity, well, we can get the velocity by looking at the rate of change of the position with respect to time. Okay, so the rate of change of position with respect to time, we'll just differentiate the other side, so you're just going to have dr theta by dt. So this value of r is just the radius, it's a constant. Okay, so r's got no dependency on t. If r had a dependency on t, as this turned round, this value here would just change like a spiral or go out and get bigger. Okay, but it hasn't. Okay, so it means you can just then take this value r out, and you're just going to end up with the d theta by dt. Okay, so now you're left with this little equation here, this ds by dt equals r d theta by dt. Okay, and these are two different things here. This is the rate of change of the position with respect to time. This is the rate of change of the angle with respect to time. So we call this here, that's the instantaneous velocity. So the velocity there is equal to r, and we give this a special name. We call it the angular velocity. So that's the angular velocity omega. So this little equation, it relates the velocity with the angular velocity. Now, here's a little aside just for a few minutes, and it might be worthwhile. This value omega is a vector quantity, meaning it's got direction and magnitude. So if we were to take, say, like a small disk sitting in a certain plane, okay, so that's sitting in some kind of plane, then this value omega, it would have a direction which would be perpendicular to the plane in which the revolution is taking place in. So, for example, if we were to take a point, let's say it's travelling in that direction there, okay, then what we can do is we can use the right hand rule. So if you take your right hand and your fingers curl round in the direction which the direction of motion, okay, in this case here it's in this direction, then the thumb will point in the direction of the vector, okay, so that would be the direction there. So that's would be our omega, and you can see why that this value of omega, which is the angular velocity, has to be a vector. So that's angular velocity, and it's worthwhile thinking about this. That's angular velocity, and that there is a vector quantity, and it's reasonable that that's a vector quantity because what you're interested in here is position. It's a positional thing, so the s by dt, that's a positional thing. So you're interested in the position of a point here, say a point in space as it rotates round. Now if I was to take this same idea here, and let's say it's this other rotation, it's rotating in the same direction, it's rotating at the same angular velocity, but if it's sitting at a different position, then it means that all the points here in this circle here now take on a different position from this one, okay, and that value omega is a vector that points in a different direction, okay. So it means that in order to get all the information we need here about this angular velocity, we need to know the rate at which it goes round, and we also need to know the orientation in order to give us all the points on the circle, okay, because that point there is different from that point there because there's a different orientation. Now we introduce another thing called angular frequency. Now it's still got the value of omega, but it's called angular frequency. Oh, my writing's terrible today. Frequency. So that's angular frequency. Now the angular frequency, you'll see it written as 2 pi f, okay, which is also 2 pi. Now frequency is 1 upon period of t, okay, so it's still in radians, and that's in seconds, so it's still radians per second, still the same units as angular velocity, but it's a slightly different thing because angular frequency is a scalar. It's a scalar quantity. It doesn't need a direction associated with it, and you can see that makes it's kind of common sense, that because if you were to take this position, this here, and that was going round at a certain rate, if I turn it on its axis so it's facing that way, it's still going round at the same rate. It doesn't matter what axis that sits on, you can pick any axis for that, okay, it's still going round at the same rate. So the rate at which that goes round is really independent of the axis in which the rotation is taking place, okay. So that's why we can say that angular frequency is really just going to be a scalar quantity, and the magnitude of this angular frequency is just the magnitude of the angular velocity here, so it's just the length of that vector. Okay, so that's just a little aside, and it allows you to see the difference between angular velocity and angular frequency. Now, if we were looking to find the angular acceleration, so we've got, just so we don't get lost here, I'll write out what we've managed to work out so far. So we've managed to work out v equals r omega. So we've got v equals r omega. Okay, now what we're interested in is the angular acceleration. So we know again from simple physics that if we were to find the rate of change of velocity with respect to time, we should be getting an acceleration. So then it means that what you can do is you can write that there as d r omega by dt. Now that's going to give us the angular acceleration. Okay, we'll just call that AC. Okay, the angular acceleration then is, well, r is just a constant, so that can come out, so it's going to be r d omega by dt. Now this d omega by dt, we're going to have to use the chain rule, because what's really happening if I draw it out like this here, what we're going to have is, as time changes, this angle changes. So we're going to have the angle as a function of time. We've got some function of time. But then, as that angle changes, the change in that angle is what ensures that we actually have some angular frequency, omega. Okay, so in order to find the rate of change of omega with respect to time, we need to find the omega with respect to theta, and then multiply it by theta with respect to time. So it's just got to use the chain rule. So we'll use the chain rule here. So we're just going to end up with angular acceleration is just going to equal r times, it's going to be d omega by d theta times d theta by dt. Okay, so that's just going to be, well, our d theta by dt is just our value of omega. That's how we've defined it, and omega can be written as v upon r, so we can just change that to v upon r. So you're just going to end up with our value of r times v upon r times d omega by d theta. So that's just going to equal, the r's cancel it out, you're going to be equal v d omega. Well, again, omega is v upon r, so you can just write that as d v upon r by d theta. Okay, now again the r's come out because it's a constant, so you're going to have v upon r times dv by d theta. Now I'll give you a little heuristic argument, and then I'll give you a little proof of this. This dv by d theta is just the same as v. Okay, now the reason I'm able to say that is that this is turning around at a constant rate. Now that means it's just turning around there at a constant rate like this. It's not getting faster and faster, then slower and slower, and then faster and faster. It's a constant rate that's going round. So if that's going round at a constant rate, that means that whenever we change this angle theta, the angle theta won't really have an effect on the velocity. Okay, it's going to be fixed. The velocity is fixed. Okay, so if the velocity is fixed, then as this angle theta changes, the velocity still just remains the same. So that dv by dt is just a constant. Okay, and the constant it is just the velocity. Okay, so you can rewrite that as v upon r times the value of v, which is v squared upon r. Okay, so you can say that angular acceleration is just going to equal the value of v squared upon r. Now that doesn't give us all the information because it doesn't tell us anything about the direction of this vector. Okay, and that's a bit kind of hand waving as well, this dv by d theta. It's a bit of a hand waving, but I'll just give you a wee proof of that dv by d theta. Okay, so let's go ahead and we'll lock that out just now. So we want to show that dv by d theta is equal to v. Okay, so that's the thing that we want to show. And again, we can rely on a bit of symmetry here. If we're going round the circle here like this. Okay, now we were to pick a point here, and we've got a velocity vector going up there, and we come along here, pick a point here, velocity vector going down there. Okay, now again that's an angle theta. Okay, and we go along there, and that's an angle theta as well. And that's v, that's v. It's traveling at the same velocity, so the length of these is exactly the same. So we can actually add them nose to tail, and we can see the difference between them. So we can take that one there, which goes up like that. Okay, and then we add it on to this one here. Now this one here, it's the same length and the same angle, so it comes back down there like that there. So that's v, that's v, and that there, well, that's the difference between these two, so we could call that delta v. Okay, so if that's delta v, and that angle there is theta, and we can go up the centre there like that, and that angle there would be theta upon 2, and that would be theta upon 2. So it means you can say, you can do a wee bit kind of jiggery pokery with this here, and you could say that the sine of that delta theta upon 2, so sine of delta theta upon 2 is that angle there, is going to be this distance here upon that distance there. Well, that distance there is delta v upon 2. Okay, so that's going to be delta v upon 2, and that distance there is going to be v. Okay, so then you can rewrite that. You could say that that's going to be, let's see if I can squeeze it in at the end here, that's going to be equal to, be able to say that delta v is going to equal 2v sine delta theta upon 2. Okay, so if we were to take the this 2, we'll take that 2 back down, then you could say delta v upon 2. Okay, so I've just taken that 2 back down there, is going to equal, well, it's going to be v sine delta theta upon 2. Okay, now if I were to divide the whole thing out by delta theta upon 2, delta theta upon 2, then I divide that whole thing out there by delta theta upon 2. So then you're able to then say that delta v upon delta theta, delta v upon delta theta, is going to be, if we take the limit of that tends towards, delta theta tends towards 0, we'll just get that in there, I'll get the limit in. So the limit as delta theta tends towards 0 of this thing here, well, that's just going to be equivalent to sine theta upon theta, and as theta tends to 0, this whole thing tends towards 1, so that whole thing tends towards 1, this just tends towards v. Okay, and that's the limit as delta theta tends towards 0, so that's just going to be equal dv by d theta would equal v, which is what we required. Okay, so that is one proof of it, but it's not the whole thing story, because it doesn't tell us about the direction, so we kind of get an intuition about the direction of that acceleration. So I'm going to show you a second proof that will give you that same value, and it might give you that intuition as well. Okay, so you could always pause the video. It's quite a long video, I suppose, isn't it? It's like 18-19 minutes. So it's been our 5 minutes, and we'll get through this other proof. Again, that's proof number 2, and again it just looks at the symmetry of the situation. So again, we'll take this point rotating round in a circle, we'll call that point P, we'll come over to that point there, we'll call that point Q, and we've got the centre of the circle here, and the centre up to there. Okay, so that's going to have your radius R, and if we were to come up to the top point there, that would be an angle of theta, that would be an angle of theta, and then what we do is we split the vector, the velocity vectors, into the components in the x and y direction. So if we call that there the y direction, then that there will be our x direction. So we could say that there's an x direction of the p component of velocity and a y direction of the p component of velocity, and the same with the q. The q is going to have an x component and a y component. So we'll just write those components out. So you can see that the velocity p, the point p in the x direction, is just going to be v cos of theta. Well, that's our theta there. Okay, so it's just v cos theta, that direction, that distance. Okay, and then you can see that the velocity at point q in the x direction, again, it's just going to be v cos theta, v cos of theta. And then you can look at the velocity of q in the x direction. So the velocity of q, now if we've already got that, v cos theta, velocity of q in the y direction, I should say. Well, we'll keep it the same throughout, okay, because I'm just going to get confused. Okay, so we've got p in the x, q in the x, so we're going to have p in the y. So the velocity of p in the y direction is just going to be v sine theta, okay, and we're going to have the velocity of q in the y direction. So what's this velocity here? Well, that's going to be minus v sine theta, because this one's in the positive direction, y direction, that's in the negative y direction. Okay, so then we can find the acceleration. So you can say the acceleration in the x direction is just going to be equal to our, going to be v qx minus v px all upon some delta t. So that's just going to equal qx, it's going to be cos theta minus cos theta, is going to be v cos theta minus v cos theta all upon delta t. Well, that just equals 0, okay, so there's no acceleration in the x direction. But now we'll look at the y direction. So the y direction is just going to give you acceleration in the y direction is just going to be equal, it's going to be our v qy minus v qx all upon delta t. So that's going to equal, well, v qy is minus v sine theta, v qx is minus v sine theta all upon our delta t. Now we can get our delta t. We know that our delta t there is going to be, well, it's this distance here. The distance there is going to be 2, it's going to be r times 2 theta. So it's going to be r2 theta. So delta t is equal r times 2 theta. So it's the distance travelled over the velocity. Okay, so times distance over velocity would be equal to that there. So we can rewrite this one above as minus 2v sine theta upon, it's going to be 2 theta r upon v. Okay, so again we can take that there and we can rewrite that. The 2's are going to cancel and the v is going to come up, so you're going to have minus v squared upon r, and we're going to have our sine theta upon theta. Now again we're going to take the limit as theta tends to 0 of all of that, and the sine theta upon theta will just tend towards 1. Okay, so that will tend towards 1, and you're just going to end up with the minus v squared upon r. So we're going to have acceleration, the centripetal acceleration equals minus v squared all upon r. Okay, now the good thing about doing that derivation is that we now have this negative direction. Okay, it's negative, that tells us that there's a certain direction associated with this vector. And you can see that the direction is towards the centre, because what we're doing, we're taking the limit is this theta tends towards 0, so it tends towards 0 in this direction, it tends towards 0 in that direction. Okay, but these just tend to squeeze in towards 0, and you can see that we worked out that there is an acceleration in the y direction. We said that there's none in the x direction. There's no acceleration, but there's an acceleration in the y direction. But this y direction, as this theta gets smaller and smaller, this y direction tends towards, if you go both sides, it tends towards this point here. Okay, so the direction there is directly down towards the centre. Okay, it's a centre seeking acceleration. If we were to do the exact same thing here round at the other, at a different angle, then again the whole thing would tend towards a centre seeking acceleration, say for that at that point there. So that's pretty much everything. We'll just write down a final little bit of equations, what the stuff that you seem to see. So one, we see that V equals R omega, okay, and that can be written as the angular omega is the angular velocity, and that is a variation in angle respect to time. And then we looked at acceleration, so we can say acceleration is equal to R. Now we replace omega there by our alpha. Okay, so that's angular velocity, this is angular acceleration, and again that's given by the second derivative of the angle with respect to time. Now one other thing that you'll also note is that we see that, well, I'll write it down and then I'll do just a quick little proof. We're just about done, just 2 minutes now and that'll be it. So we sometimes see the third one, that A equals minus R omega squared. Okay, so that's the third one there. Okay, and that's omega, which is d theta by dt, so omega squared would be that whole thing squared. Okay, I'll just write it down. So it's going to be d theta by dt squared. Remember, this here is different from that. That's the second derivative. Okay, that's the first derivative squared. Okay, so don't mix those up. And we can see that there. If we were to write what we did earlier, A equals minus v squared upon r, and we were able to know that v equals r omega, so we can say that v squared would be r squared omega squared. We can take this, pop it in there, so we'd say A equals minus r squared omega squared all upon r, which equals minus r omega squared, okay, which is what we've got up there. Okay, so that's everything. I think I've done that one to death. Hopefully that's allayed any fears or any questions you had about angular velocity, angular frequency, angular acceleration. Okay, thank you, goodbye.